In this tutorial, we will be discussing the quantum numbers and how to determine them. So what exactly do the quantum numbers tell us? They tell us the location of the electrons in relationship to the atom's nucleus. They're like a home address for them. They specify the area an electron occupies in relationship to the nucleus. Each quantum number describes an allowed energy state of the electron. The Pauli exclusion principle indicates that no two electrons can have the same set of quantum numbers. So every electron surrounding the atom's nucleus has its own set of quantum numbers. And this next point is extremely important. Each orbital can only have a maximum of 2 electrons with opposite spins. So in other words, one's going in one direction, the other one's going the other. And that's why when we're doing electron configurations, you can only put 2 electrons in the s orbital. And we'll go over that in a little bit in more detail. So there's 4 possible quantum numbers. N is the principal quantum number. It indicates the energy level the electron occupies. So the nucleus is in the middle, and the electrons are traveling outside the nucleus in rings or shells, which is why they're also called shells, around the nucleus. And those are whole number integers like 1, 2, 3, 4, and so on. Those are N's. Within those shells are subshells with different specific shapes. This is the angle quantum number. It indicates the orbital shape. Values of L are determined by n minus 1. And that's where we get the S, P, D, and F from. S is 0, P is 1, D is 2, and F is 3. You would take the n and subtract 1, and it goes all the way down to 0. So L is dependent upon n. M sub L is the orientation of the quantum number, indicates the area of the electron occupies. Values of M sub L are determined by a positive or negative value of the L. So M sub L is dependent on L. So it can be positive L down to 0 down to negative L as whole number integer possibilities. It explains why there are 1 type of S, 3 types of P, 5 types of D, and 7 types of F orbitals. The magnetic quantum number, which is the final one, indicates the spin of the electron in the orbital. Electrons can spin with a magnetic field or against a magnetic field. And it's a value of plus 1/2 or negative 1/2. And it's indicated by an arrow. So here's L. If L is equal to 0, it's an S. If L is equal to 1, it's P. If it's 2, it's D. And if it's 3, it's F. So when we're talking about 1s2, 2s2, 2p6, 3s2, so on and so forth, this is the L, the letters. The first one is N. This here is L. So, for instance, L is equal to 0. That means M sub L is also equal to 0. And that's telling me that it's just this shape here. There's only one possible shape. Every energy level has an L, has an N, has an S orbital. S orbitals have the lowest energy within the principal energy level, and S orbitals have a spherical probability plot. With N's, 2, 3s, remember every energy level has an S. They encompass one inside of the other. And these are the subshells. here's P. So this is L is equal to 1. So this means that we have M sub L equal to 1, 0, and negative 1. Notice we have three numbers here. We have three possible orbitals it can be in. And when we look at our electron configurations, for instance the third energy level, that's N is equal to 3. The P means that it's L is equal to 1. And this is telling me that there's 6 electrons in there. Each one of these can contain 2 electrons. And that's how we come up with 6. 2 electrons in this one, 2 in here, and 2 in here. And here's D. This is for L is equal to 2. That means M sub L are going to be 2, 1, 0, negative 1, negative 2. Notice there's 5 numbers here. There's 5 possible orbitals. That's the correlation. Each D as a whole can have 10 electrons. Well, that's because there's 2 electrons in each one of these orbitals diagrams. Alright, so let's break it down and look at the numbers and focus on those. If N is equal to 1, that means L is N minus 1, so 1 minus 1 is 0, and that's how we got this number here. And then M sub L is plus or minus L down to 0. Well, since it's 0, plus or minus would be 0. If N is equal to 2, that means L would be 2 minus 1, which is 1, down to 0. So here's 1, here's 0. L is equal to 1 tells us it's P. L is equal to 0 is telling us it's S. Just like L is equal to 0 here is S. M sub L would be, for this one, 0. For this one is plus or minus, plus L to 0 to negative L. Well, that means it's 1, 0, negative 1. And that's how they got these numbers here. For energy level 3, that's 3 minus 1, which is 2. 2, 1, and 0 are our options because we go down to 0. 2, 1, and 0. 0 tells us it's S. 1 tells us it's P. 2 tells us it's D. So we take this down here, and we say M sub L is positive L to 0 to negative L. So if L is 0, that means 0 is our only option, so this is our only orbital possible. If L is equal to 1, that means it's going to be 1, 0, negative 1. And those are our 3 orbitals there. And then for L is equal to 2, that means it's going to be 2, 1, 0, negative 1, negative 2. And that's where we get these numbers from. Notice there's 5 of them. Now the only one we haven't discussed here is M sub S, which is going to be plus 1/2 or minus 1/2. And that's talking about the electrons themselves. So if this is 1s2, we have 1 electron going one way, 1 electron going the other way. 2s2, 2 electrons in that box. The arrow represents the electrons. 2p6, 1, 2, 3, then you go back and pair them up. 3s2, opposite directions. 3p6, 1, 2, 3, go back and pair it up. Let's say we have 3d5 here. We're going to actually put them all in one box, and then we're going to leave it as that. So electron spin and magnetism. If the substances have paired spins, so when we look back here, this is what we're talking about, paired spins. If the electrons are all paired up, they are not attracted to magnetic fields, and that's called diamagnetic. If they're unpaired electrons, which is why I left 3d5 deliberately rather than 3d10 to show you this is the unpaired group. If it has unpaired groups, that's going to be attracted to magnetic field, and that's called paramagnetic. Alright, so let's practice this a little bit. Which of these are not possible? Well, the first letter is N, and that just has to be a whole number. And all four of these are whole numbers. The second letter is L, and that's N minus 1 down to 0. So that means these have to be less than N. So 2 is less than 4, 4 is less than 8, 1 is less than 2, and 3 is less than 0. So we're okay there. This one is M sub L, and it has to be positive L to 0 to negative L. So it has to be in the range of this. So it has to be between 2 and negative 2. And negative 1 is within that range. The next one has to be between the range of 4 and negative 4. And that negative 2 is within that range. The next one has to be in the range between 1 and negative 1. 2 is outside that range. So this is incorrect. And 0 has to be in the range of 0. Finally, this is M sub S, and it has to either be positive or negative 1/2. If it's any deviation of that, it would be wrong. This is the only one in this set that's wrong, and it's because of M sub L. And then finally, let's talk about breaking the electron configuration down to quantum numbers. So if we want to break this down to 3p, we know that 3 is N and P is L. And this means L is equal to 1. So that means our first numbers is 3 and 1. So we have M, L, M sub L is going to be positive L to 0 to negative L. So that means from here we know that L is 1, so it's going to be 1, 0, negative 1. So there's 3 possible orbitals there. So we can say this one's 1. Then let's do the next one. 3, 1, 0, 3, 1, negative 1. The last one is M sub S, and that's always going to equal plus 1/2 or minus 1/2. That means we can break all 3 of these into another set. So this can go 3, 1, 1, positive 1/2, 3, 1, 1, negative 1/2. This can go 3, 1, 0, positive 1/2, and 3, 1, 0, negative 1/2. And finally, we can break this one down to be 3, 1, negative 1, positive 1/2, and 3, 1, negative 1, negative 1/2. So we actually have 1, 2, 3, 4, 5, 6 possibilities quantum numbers. And if you think about it, this makes complete sense, because what's the maximum amount of electrons that can be in 3p? The answer to that is 3p6. Since there's 6 possible electrons, here's the 6 possible mailing addresses, home addresses for those electrons. And that's how you predict quantum numbers.